everyone. Welcome to tonight's version of our FRC workshop series here in Australia. Tonight, we are really fortunate to have somebody from the Barker Redbacks team 4613 here. Alistair is here to talk about how to make parts with the CNC. Alistair, how long have you been doing FRC?
I've been doing FRC since 2013, so I think that's seven years. Yeah.
Yeah, and how long have you been working on?
A while.
How many years have you been working with these CNC?
So we only really started using it in 2016, and I've really been involved in the process since about 2018. So still a couple of years.
You got years of experience on this.
Yes.
So we're really looking forward to it. And you have the floor.
Thank you. So what is a CNC router? A CNC router is a computer numerical controlled machine that can move a rotating spindle to specific locations or coordinates, allowing it to follow lines, drill holes, and create curves. They move in the X, Y, and Z axes. What can a CNC router do? A CNC router is very effective as it can machine most commonly used FRC materials. These are typically plywood, MDF, and hardwood, which are normally used for bumpers or field construction or prototyping, polycarbonate, HDPE, ABS, Delrin, and most other plastics, which are normally used for robot parts, as well as aluminium sheet, thicker aluminium plate, and aluminium extrusions. Together, the plastic and the aluminium will make up probably 95% of a robot. How does it differ to a CNC mill? It can be quite easy to look at a CNC mill or a CNC router and think that they're quite similar, but there are some major differences. The spindle RPM is typically higher on a router than a typical CNC mill, which means it's ideal for cutting 2D parts out of aluminium sheet. A CNC router will also typically have a larger work envelope or area, allowing you to use larger sheets of material with less wastage. The table does not move on a CNC router, so material can be much larger than a machine without issues, such as the material actually having to move around. The main disadvantage is that there are slower travel speeds and most don't have a tool changer. So you may know that there are a couple of different ways of creating parts. So you could have a water jet, a laser cutter, a plasma cutter. So those are strictly 2D. So those will cut along your line, and those are restricted to cutting all the way through the material. They cannot simply cut halfway through. The other difference between, say, a water jet or a laser and a CNC router is a water jet or laser will cause a taper or angle on the edge of parts. So a CNC router is better for precision and for bearing holes, which normally need to be quite accurate for the bearing to sit in them correctly. Our CNC router can also cut thick aluminium that a laser cutter or plasma would struggle with. A CNC router can also cut plywood and plastic better than a water jet cutter or a laser. And a plasma cutter is strictly for conductive materials only. However, a CNC router will typically have quite a bit more setup time than a water jet, laser, or plasma. This is because on a CNC router, the cutting tool, the router bit, is actually pushing against the material, meaning that the material needs to be properly clamped and held. This is known as work holding. Additionally, a water jet, laser, or plasma will typically just cut along a vector line, such as the edge of your part, off a preset distance. But a router will need to have the correct tool and the feed and speeds selected for it to operate correctly. This means that it's a lot more setup time. Having a CNC router or any CNC machine can be very beneficial for your team. It allows the introduction of a CAD-focused robot design approach, such as what we have here on the Barker Redbacks. It provides students with more design options and more design flexibility, rather than having to be restricted to parts that you can make by hand or parts that can be purchased from a COTS supplier. Rapid iteration The machining and testing of multiple mechanism versions in one day is also possible. If you were, say, relying on a sponsor or a friend of the team who has a machine, this may be quite a long, drawn-out process, meaning that you wouldn't be able to prototype regularly. Instead, with a machine in-house, you can make several mechanisms per day, which greatly speeds up your prototyping process and allowing you to have a better, more effective end robot product. Sponsors or outsourcing can lead to delays, and especially if you're outsourcing through a paid company, it can be quite costly. And you may quickly find that the investment in a CNC router or similar machine would pay off. Also, you will be able to reduce your spending on basic COTS parts that you would typically buy from suppliers like AndyMark, such as tubing or gussets. There are some considerations when choosing a router. CNC routers and other machinery are potentially dangerous. So you need to check with your school to make sure that you're compliant with safety and electrical standards. The other thing is that very low-cost machines typically aren't suitable for machining aluminium as they are not rigid enough. Pick a machine that has proper linear rails, not V-wheels or rollers, and not belt-driven. Ball screw or rack and pinion machines are best. Work area. This is important to consider. Different teams will have different requirements, and larger machines are typically more costly and require more space. If you're an FTC team, you wouldn't need to machine parts which are as big as an FRC team. Similarly, if you're an FRC team and you felt you didn't need a full-size machine, you could go for a smaller one and still usually be able to machine the vast majority of parts on that machine. Here are some considerations when choosing a CNC router. There is a machine called the Omeo X8220L, which is a good option for machining aluminium, but you'll want to check that it meets the necessary standards for your school. Other small machines are available from Blue Carb CNC or CNC 3D in Australia. The Blue Carb Turbo is a good option for machining aluminium. Although I haven't used it myself, I've seen good reviews of it. If you have the space and budget, a large 4x4 foot or 4x4 or 4x8 router is likely the optimum manufacturing solution for FRC teams. This allows you to process sheets of material with minimal wastage. Sheets of aluminium, sheets of plastic, sheets of wood normally come in a sheet size which is 4x8 foot or 1200 by 2400 millimeters. So going for a machine which can fit at least half a sheet is an effective way to manage material, and it allows you to keep material in these larger sizes. It also allows you to make parts such as belly pans or very long tubes, which you may not be able to do otherwise. Multicam is a good and popular option and is already used by a number of FRC teams in Australia. So now I'm going to provide a brief introduction to router tooling. Different materials require different tools if you want the best results. Cutting aluminium, wood, or plastic is quite different. For FRC purposes, the edge finish on plastic and timber is not critical. So tools intended for aluminium will work fine and help reduce inventory and changing of tools. Typically, the flute design of a tool for aluminium will be slightly different to that of a plastic tool. Additionally, once you start using a tool for aluminium, it can become chipped. And while you might not notice this when cutting aluminium, on plastic, this will lead to a poor edge finish, which again isn't critical for FRC team use. Larger diameter tools are stronger, so they can cut faster and deeper. But smaller diameter tools, on the other hand, such as 1/8, 3 millimeters, or 4 millimeters, are able to cut the outside of parts and drill or bore holes. This means that you don't need to worry about changing tools mid-cut or purchasing a machine with an automatic tool changer. For thin plastics such as 1/16 polycarbonate, a down-cut single flute bit is interesting as it puts downwards pressure onto the material, preventing it from lifting up and flapping around. So if you see here, the actual tip of the tool is actually below the actual cutting bit, which means that the chips are pushed downwards and the pressure is downwards, stopping that material from moving around. For plywood, MDF and hardwood, there are multiple options which work well, as it is quite a forgiving material. A compression bit is the best option for plywood. This puts equal pressure both up and down, preventing tear out of the veneers on the bottom and top of the sheet material. Single straight flute bits are normally 2 flute, and they are a versatile economical option. They do not put pressure upwards or downwards. Instead, they put even pressure next to the material. This also helps keep material in place while you are cutting it. It's important to choose router bits with a cutting length that is not larger than needed. The longer the tool, the more likely it is to break. And this also reduces maximum cutting speeds. It is rare to have to use aluminium thicker than about 12 millimeters or 10 millimeters. So pick tools which have a cutting length of between 12 and 15 millimeters to give you a bit of a leeway in case your tool isn't quite set correctly. The best router bits for aluminium are single flute upcut bits, as these lift chips out of the cut and have a geometry that makes them ideal for drilling and boring holes. If you see here, you'll see the quite pronounced tip on the tool, which is effective for drilling and boring holes. Additionally, the inside of the flute is polished. This means that there is minimal chance for chip welding to occur, which is where the aluminium remelts and gets stuck to the tool. So this is an example of a single flute upcut bit. There's several different options for these tools in Australia, with aussieboys.com, which is my business, being the best value option. But there are a number of different options. Now I'm going to talk briefly about collets. CNC routers use expanding and compression collets to hold tools firmly with minimal runout. This is a ER32 collet. As you can see here, the tool fits in the end, and then the pattern around here, the slots allow it to squeeze and compress the tool when the collet nut is done up. These collets are typically ER20 or ER32 depending on the machine spindle, but they can also be smaller or larger. Hobby machines will typically have ER20 or ER16 collets, and these can't hold tools which are as large. For FRC purposes, it typically isn't needed to use tools larger than about 13 millimeter. So an ER20 collet or even an ER20 collet would be suitable. Additionally, it is rare to use tools larger than about 6 millimeter. So if your machine has an ER11 or ER16 collet, that's also okay. Collets compress when you rotate the collet nut into the tool holder or the spindle. So they have a specific size range. This one has a range printed of 3 to 2 millimeters. It is better to use a collet that requires the least amount of compression for the tool. So if you were to have a 6 millimeter tool, it would be best to try to use a 6 to 5 millimeter collet, even though the smallest tool that will be able to hold, the smallest diameter tool to be able to hold with your 5 millimeter diameter. Using a 6 millimeter diameter tool in the 6 millimeter collet helps reduce runout and will help improve the life of your collets, as the spring steel will eventually effectively lose its memory and will get stuck and will lose its springiness. The tool needs to be at least 3/4 inside the collet. Otherwise, what can happen is the tool can effectively move like this inside the collet, which can cause chatter and increase the likelihood of tool breakage, which can be quite expensive and annoying. Here's an example of how to install a collet into the collet nut. So it's a common mistake to actually try to put the tool into the collet before you put the collet nut around the collet. So what you typically do is you put the collet, you get the collet nut, you push the collet into the collet nut, and then you would then, in step 2 here, you would insert your tool. CNC machines require CAM instructions, usually in the form of G-code, which tell the machine where to go and what to do. CAM is the necessary bridge between the 3D model of your robot part and the CNC router itself. There are multiple options available. Fusion 360 has a good built-in CAM or manufacturing tab, and it is free for academic and educational use for Australia. There are also a range of other options, such as NRoute and Vectric, which are suitable for routers and have a different workflow. These softwares typically work in 2D, whereas Fusion 360 will work in 3D. If you're using Fusion 360, you can import your CAD files from SolidWorks, Inventor, or Onshape, and then do the CAM. Additionally, if your part is designed natively in Fusion 360, it is even easier. Although Fusion 360 is a little bit more time-consuming to set up your CAM, the advantage of Fusion 360 is that you can actually modify your part without needing to redo your CAM. So if you realize, oh, this hole is in the wrong position, or this pocket cutout needs to be larger, you could actually change that once you've started machining without needing to start again. For aluminium, it is important to keep tools within a specific chip load or cut per tooth. This stops chip welding or the tool gumming up from getting too hot, which effectively causes the aluminium to remelt inside. It's interesting, feed rates are a bit of a paradox. You might think that your machine isn't working effectively because you're running too fast, where it can actually be the opposite. Decreasing the feed rate can actually make things worse if you are having issues. Chip welding or tool gumming up, as I just mentioned, can be caused by running a machine too slowly rather than running a machine too fast. So decreasing the speed can actually be negative in this circumstance. The depth of cut depends on the machine rigidity. So depth of cut is how much you can cut at once. So if you were cutting a piece of 3mm aluminium sheet, which is common for robots, some machines and tools may be able to cut all 3mm at once, while others may only be able to cut, say, 1mm at once. If your machine isn't rigid or isn't powerful, you can still use proper feed and speeds, and you can simply lower the depth of cut. It's a common misconception that it's important to use the entire tool to avoid premature wear. But carbide tools typically don't really wear in aluminium, so don't worry about using just the bottom few millimeters of the tool. So going back to the feed rates, if you're having issues with your machine, it can be helpful to decrease the depth of cut and increase the speed, because it's important to keep the tool within the specific chip load. And this allows it to properly evacuate the chips and evacuate the heat from the tool. There are two sizes of tool I like to use in stock. These are 4mm, in which case you would start typically about the top speed of your machine, around 1500 millimeters a minute and about 1mm depth of cut. As I've mentioned previously, a 4mm tool is a good option because it allows you to both cut the outside of your parts, drill or bore internal holes, and do most cutouts. A 6mm tool, on the other hand, is going to restrict you. While it can be faster for cutting, once you factor in the time that it takes to change the tool, start another CAM program, it can take much longer. You can go faster than this, but you will typically need a misting system. So a misting system is basically a lubrication system. At a very basic level, it does two things. It provides lubrication to the tool as well as cooling. It can commonly use that you cut dry, where you might just use compressed air to provide some cooling and chip evacuation. But this does have some limitations, and it can actually cause your tools not last as long. Now I'm going to quickly go over some tools which I like to use. And I'm going to show you some robot parts. So I can make this full screen.
Do you need me to do something?
Yes, are you able to change it so I can show the camera, so the camera will be full stream on the full size on the stream? So I can show some examples of parts.
Like that?
Sorry. I'm having trouble doing that from my end.
So I think I just put us near the top.
Can you make it larger so it'll be easy to see?
I think that's about the best I can do.
Okay, that's fine. So here's some example of parts. So as you can see here, this is quite a thick aluminium piece. This is made from 10mm aluminium. And you can see on this one, the edges are actually quite straight. And so if you were trying to cut this with a laser or a water jet cutter, that would create a problem. Additionally, you can see that this part isn't simply a 2D part. There are small recesses here, which act as a shoulder to fit another part into. So this is more of a 2.5D part rather than a 2D part. And here are some other examples. Here's another part, which is a plate part, which is quite thick. And typically, the only limitation for thickness of material is the tooling. So if your machine can cut aluminium, which is 3mm thick, you will generally be able to cut material which is 10 or 12mm thick. But you would simply have to do it at a slower rate with a lower depth of cut. Here is some 6mm or 1/4" aluminium, which is quite common for use in gearbox plates. Here you can see that the CNC router was able to make small pockets here, which act as venting for the motors. And again, you can see another example of a 2.5D pocket here. Another interesting thing that you can do with CNC routers is you can create a gear tooth profile. It can be quite difficult to do this with other means, especially manual means, but with a CNC router it is possible. Something to consider here is that you need to have a tool which is small enough to be able to fit into the tooth profile. In this case, even a 4mm tool does not really fit. And for this gear especially, you would need to use closer to a 3mm tool, which I believe is what I used for this. But you can see that with these, with the rack and pinion here, it actually moves quite nicely. So that can be helpful for arms or say a turret on your robot.
Alistair, if you stop sharing your screen, I think you will get bigger.
Okay, I will. Yes, I am. that works. I think that's better now. So, and here are some other gears. You can see the difference between these two. And again, this could be done with a 6mm one. And these gears were from our 2018 robot and used for the arm. And so it was quite good to be able to make something like that in-house in our machine. The other example you can see here is hex. So typically we use a 1/2-inch hex shaft for most applications on our robots. So this hex bore was created by doing a 1/2-inch round hole and using a hex broach. But hex broaches can be quite costly. Additionally, it can be quite difficult to properly align the hex broach with the teeth of a gear or say a sprocket if it is required. In this case, it wasn't. A CNC router can use the router bit to create a hexagonal shape with rounded corners or radius corners. This would be okay for piloting a thunder hex shaft through, which is a hex shaft which is effectively modified to have round edges. Additionally, you could also, if you wanted to fit a standard hex shaft in here, you could also do what's called a dog bone or a relief in the corner, which is where you take away the additional material using a router bit. Again, you're not restricted to just aluminium. Here's a polycarb part which was done on a CNC router. And here's a thicker polycarbonate part which was done on the CNC router as well. Again, you can see the example of the 2.5D pocket which was done here. And tubing is also possible. So typically we like to use thicker aluminium tubing and then do weight saving, as it is a lot stronger for bearing holes and specific mounting locations than thinner tubing. This tubing was pocketed on all sides using a fixture or jig on the CNC router that we have. So a CNC router provides a lot of different options. So now I'm going to provide a brief introduction to cam generation on Fusion 360, which you would typically need for running your CNC router or even another CNC machine. Now I'm just opening up a Gusset. Apologies for the delay. I was under the impression that I had this open already.
Right, and remember, you're gonna have to reshare your screen now.
Yes, I'm just trying to find to open up the model that I had, but
Oh, good.
Apologies.
It's fine.
I'm having to troll through my computer. All right, so here is a Gusset, which I've just opened up. So I imported this one from a step file, similar to what would be exported from SolidWorks, Inventor, or Onshape. And again, if this was a native Fusion 360 file, then that would also work. So this Gusset has a couple of features on it. So it has the holes, which need to be 4 or 5 millimeters, and it has the perimeter. Additionally, some parts may also have a bearing hole, which comes with additional requirements for the machining. So the first step, once we've opened our step file of our Gusset or other part, is to change from the design to the manufacture tab. As you can see here, the normal menu that exists within Fusion has now disappeared. And now we have a number of tools which we can use to create CAM, files, or G-code later on for our Gusset. So the first thing to do is to click New Setup, or I like to click New Setup here. Typically, with conventional CNC machining on a CNC mill, you will start with a piece of bar stock or rectangular stock and machine away the rest of the material. But on a CNC router, we're lucky. We can simply cut around the outside. So the first thing we're going to do is we're going to set our stock as from solid, as this will allow us to simply cut around the outside, which minimizes wastage. As we can see here, it also shows us the overall dimensions of our part. And we can click OK. Back here, we do have the option of changing the Z-axis direction. So if you're going to be CNC machining this or doing this on your CNC router, you need to make sure that your Z-axis is facing upwards, as the Z-axis correlates to the up and down motion of the machine spindle. You could also change the origin location. But for Mach 3 CNC machines, I typically prefer to leave the origin in the standard location. So we can click OK. So our first step is going to be to cut around the outside. So we're going to click 2D contour, or this one here. And we can click this bottom edge. We'll also have the opportunity to select and add a new tool. I already have a number of tools in my library, but I'm going to add a new tool. So I click my setup, and then I click new tool. So here we have quite a few different options. A router bit or a single flute router bit is typically known or referred to as a flat end mill. So we're going to click flat end mill. Then you would add a specific name for your tool. In this circumstance, I'm going to do 4mm single flute. And it's important to add this name so we can quickly identify the tool later. Next, we need to enter the information about the cutter or the dimensions of the tool itself. So again, make sure we've got flat end mill selected. We want to click one flute, and it's optional, but I typically like to change the material to carbide. Then we can enter the diameter as 4mm, the shaft diameter as 4mm, the overall length to 50mm, and the length below. These don't really matter. Effectively, Fusion 360 is quite a powerful software, so it will try to help you from creating crashes on your machine. But that typically doesn't really matter on a CNC router. But for example, if you were trying to cut material which is 50mm thick and your tool was only entered as 40mm thick, it'll prevent you from doing so and show you a warning. We're going to enter our flute length of 12mm here. Then we're going to move over to the cutting data, which is where we enter the feed and speeds for the tool. So we're going to enter 24,000 RPM. And as I talked about earlier, the 1500 millimeters a minute. And you can leave the lead in and lead out feed rate as so. Additionally, the ramp feed rate and plunge feed rate can be left. So now we're going to go accept. And we're going to select this tool that we've just created. And now you'll see that most of these feed rates and speeds have actually turned up inside our menu. Then we can go to geometry and double check that our outside contour is selected. As I talked about before, we typically don't cut, especially on small machines, we typically don't cut the material all in one pass. So you would go to passes and select multiple depths and enter the maximum roughing step down as 1 millimeter. Additionally, if your part has a large number of curves on it, for example, it's a very large arc, you will also want to activate smoothing, as it effectively will help the machine approach and go around the curve. Because if you think about it, the machine itself is trying to go to set coordinates. And so if your curve is very, if you're telling the machine to make the curve very precise, it will struggle to go to all of these coordinates, which will slow things down and create problems. So we're going to go OK. And we can see now that a toolpath will be created. In this circumstance, because we entered the maximum step down of 1 millimeter and our material is about 2.3 millimeters thick, it will have to go around 3 times, with the final pass being a small 0.3 millimeter cut. And now we can watch the simulation inbuilt to Fusion to see what's going to happen. So the tool leads in or plunges into the material, does 1 pass, comes around again, does another pass, then it goes for the last pass. And after that, it does what's called a lead out, where it raises up. Now we can add boring or drilling of our holes. So we would select, if we wanted these holes to be 5 millimeters, for example, even though they're 4 millimeters in the CAD and our tool is only 4 millimeters, we would select a 2D bore, and we can select our hole. Then we can select what's called select same diameter. So what a bore does is a bore uses the outside of the tool. So rather than simply going down vertically, plunging down vertically, the bore will make the tool move more like in a helix, which is much better for the tool and reduces load. Because typically tools themselves, especially flat end mills, are designed for cutting using the outside of the tool rather than simply plunging down. So for this, I'm going to select stock to leave to be minus 0.5 millimeters, which is going to make our 4 millimeter hole be 5 millimeters, and I'm going to click OK. As we can see now, we can see the helix, which is created as the tool plunges. Typically, it's better to drill or bore the holes or do other pocketing operations before you cut the outside of the part. So I'm actually going to go and drag this up to be above here. So now if we watch what's happening and we run our simulation, it's going to do the boring where it's rotating in a bit of a helix. And then after that, it's going to move into the cutting. So most CNC routers, especially small ones, will run off a controller called Mac3, which is effectively where you use a laptop or an old desktop computer to actually function as the machine controller. So which means we need to actually, and we need to convert our Fusion CAM into G code, which is actually readable by that controller. So different CNC machines will need different post processors. So on the multicam machine we use here at Barker, I'll use a different one to say the machine I use at home. So to do our post processing, you simply select the setup, which means you select the files that you want, or you can also double select both, which means you've selected both operations, and you would click post process. I have my post processor selected here, but otherwise you would scroll down in this box until you go to the one which reads CNC router parts Mac 3 mil. And then you would simply type in a program name or number and click post. Once this happens, a text editor is going to open up, allowing us to see our G-code. Now we could actually edit some specifics in here. So if I have a machine with a tool changer, I could actually change the number of the tool that I want. Additionally, you could also change the speed that you want to say 18,000 RPM instead of 24,000. And we can see here, these are all the coordinates that the machine is going to in order to cut our part out. So the first lot is the boring, and the second is the 2D contour. And so there are about 400 lines of G-code for our part. And typically, because the origin remains the same, you could, as long as you could position this on your machine, say run the boring operation, and then actually do the contouring operation in a separate file afterwards. But again, that depends on where you actually set the origin on your machine. So now I will go through that again on another part. So this part is a little bit different as it has holes, an outside to cut, and the bearing hole. But we would approach it in a similar fashion. So we select Design, Manufacture, Setup. We leave our Z and our origin in the same location. We click From Solid, we select our part, and we click OK. Bearing holes need to be quite precise for the bearing hole to fit easily. And whether you want a press fit or a loose fit will change what size you want to cut the bearing hole to. We typically CAD our bearing holes to be slightly larger. This reduces the need for additional work in the CAM program. So typically as a 1.125 inch bearing is about 28.54 millimeters in metric terms, we CAD our bearing holes to be about 28.6 or 28.65 millimeters, which ensures a proper even fit. It is quite common if people want to do a press fit, but we like to actually leave it a sliding fit so that we can easily do maintenance and remove the bearings after, as they can be quite costly. So for this one, we're going to select 2D contour, and we're going to select the bottom contour. And we're going to select 2 passes as before. And we're going to select the tool that we added previously. as you can see, we still need to do 3 passes to cut this bearing hole. Another way of machining that you would use, and another function in Fusion that you would use if you were, say, wanting to only cut halfway through your material, is known as a 2D pocket or 2D adaptive clearing. So 2D adaptive clearing is essentially a toolpath that will helix or ramp into the material and then slowly cut around the outside with a chosen width of cut, which is basically how much it cuts away at a time. So we can select 2D adaptive clearing, select our bottom contour, enter the optimal load that we want, and click OK. And we can see here what happens. So if we watch the simulation, it is going to slowly ramp in to our material and then cut around the outside. You could use this for a typical bearing hole when you are cutting through all the way, but it does tend to take longer as you're effectively having to turn all the material into aluminium chips, whereas you would normally just cut around the outside of the bearing hole, leaving a small dump in the center. Something to consider is that on thicker materials such as thick or 10mm aluminium, the extra little bits in the middle can be quite hazardous when you're cutting through and they can jam the tool. So sometimes I like to actually machine away all the aluminium inside before doing a final finishing pass. So for the finishing pass, you would set up a separate 2D contour and you would go, okay, and this is basically just going to be skimming the inside. So after we've done our 2D contours, our adaptive clearing, it is simply just going to come and skim the outside and making sure that it's the correct size. And so this would also allow you to easily dial in the size of the bearing hole without needing to run the entire operation again. And again, now I'll show you what you can use if you want to make your bolt or rivet holes the exact size with a tool. So these holes here are 4mm and our tool is 4mm. So I'm going to select these ones using the select same diameter tool and select drill. I'm going to reduce our plunge feed rate to about 100mm a minute. If you see now, when I run our nice little simulation, the tool is effectively plunging straight in without any helix. But you may notice that the tool is not actually going all the way through. So we want to change in the info, sorry, in the drilling menu, we want to go edit, and we want to select drill through bottom. And I like to add this, I like to add about 1mm to this to make sure our hole is nice and clean. So as we can see here, it's going to be drilling through a little bit extra down the bottom, and that will effectively leave a small divot in our spoil board, which is typically MDF and is disposable anyway. So that is 2 parts that I've shown you how to do the cam for in Fusion. And now I will answer any questions which have been submitted.
Hi, so that was great. We have a few questions for you.
Great.
So the first question has to do with the sacrificial baseboard on the CNC machine.
Yes.
Is there any special material that you'd recommend using? And what sort of methods do you use to secure your metal to the baseboard?
So we typically use screws or clamps. So if you have a sheet of material, say with your spoil board, you would typically use like something low cost, like MDF or plywood, or you can use like a laminate material as well. You basically bolt that or clamp that to your machine, and then you would put your aluminium sheet, which is normally smaller, and secure it using screws afterwards. Screws can end up taking up some of the material if you're not careful, and they can add or lead to a bit more wastage. So clamps are also another option, is once you remove the clamps, there is no hole or damage to the material. So yeah, anything basically low cost is a good option for the spoil board. Some materials like MDF, if you're using a lot of coolant, they can end up swelling up because MDF is basically absorbs moisture. So other things you can use would be like a HDPE sheet you can get, but that's typically a lot more expensive. Yeah.
Great. Next question is a vacuum necessary for chip removal?
So a vacuum is not necessary for chip removal. So typically you can either vacuum the chips up as you go around with a vacuum cleaner, or you can wait to the end and then clean up all the mess with like a dustpan and broom or a small shop vacuum cleaner. You can get a little like wet and dry vacuum cleaner, and that's a good option. You don't need anything fancy, just something to pick up, which will pick up the little aluminium. And yeah, I normally like to wait until the end to clean up the chips, get it all in one go.
And you know, if you do it at this time of year, you'll have a little bit left in your hair and you'll look a little bit like a Christmas tree.
Yeah, I always end up having a lot of aluminium in my pockets, you know, in your shoes.
Yeah, those are painful. All right, next question is, do you recommend training all of your mechanical team to be able to operate the CNC, or do you just train a few people and have them be highly experienced on the machine?
That's a fantastic question. I think if you're wanting to introduce sort of the idea of CNC, it's good to show everyone how it works so everyone can understand the limitations. So think about if you've got a lot of students designing parts with very square corners, you know, or text, which requires a very small tool. It can be quite helpful for people to understand the process so that they keep you happy and they make sure that what they design is actually possible to make. But otherwise, I think it is good to probably have a few key people which you set aside and you say, you know, you're going to be doing most of the machining, because that means that you can give them the most training, make sure that they're being as safe as possible, and making sure that they understand the machine properly, because it can take some time to understand what to do and what not to do, especially when setting up the cam or using the machine. So yeah, I would suggest just having a few core people, but getting everyone involved, showing everyone how it works is great, and you know, it's really part of the whole STEM aspect.
I think that's all the questions that
are. Oh, great. Okay.
So do you have any parting words of advice?
Yes, my email was in the slide somewhere, and I'll bring it up again now. So yeah, if you're looking for a machine or you're looking for tooling, I can help you with specific recommendations. And it can be helpful to have someone who sort of understands a bit more of the FRC requirements. And again, we also have Lyle, who's also quite familiar, and I can give you his email as well. But yeah, send me an email and then we can provide some more direct support to you. If you're in Sydney, I'm very happy to go out and help you set up your machine, help you get your machine working well for you.
Awesome. Well, look, that was fantastic. I think there was some really, really great information there. I think that you have definitely inspired some people who maybe haven't used a CNC before to take that first step.
Yeah, it can really
magic work.
Provide a big benefit to your team, and also really sort of improve the whole design process and engineering aspects. Yeah.
Yep. So thank you so much.
Okay, thank you.
We also have to say thank you to Ian from IC Robotics, who's been monitoring the chat and making sure the questions got fed through. So thank you, Ian. And this is the end of our FRC workshop series for the year. So I hope that everyone has enjoyed it and have a great holiday season. And we'll catch you in 2021.
Yeah, thank you. See you guys all next year.
Bye.
Bye.